The last thing you guys are going to be learning for Unit 10, all about acids and bases, is something called a titration. Now, you're going to be happy to know that titration is not a calculation. So again, kind of relax on that front. But a titration is instead a technique. It's a technique that we use in order to identify the strength or the molarity of an unknown solution. Now, that solution could either be an acid or it could be a base. It works both ways. But this technique is going to help us to identify what strength or molarity is that unknown solution. So what we need to do first is go through some definitions, and then on the right side, I'll show you the setup and how we actually do it. So an unknown is going to be a solution with an unknown molarity or strength. Unknown concentration. And again, whenever I say concentration, really what I'm talking about is a molarity, which is capital M for molarity, right? So that's our unknown. Typically where that's going to be located is at the bottom. And you'll see that right here in the pink flask at the very bottom. That's our unknown. We don't know the concentration of that. Our standard solution is a solution with an known concentration. Now, these have to be the opposite. And what I mean by that is if our unknown is an acid, then we need to use a standard solution of a known base with a known base concentration. Conversely, if our unknown is a base, then we need to use a standard solution of a known acid at a known concentration. You have to know the standard, but you don't know the unknown, which is why it's called that. And again, they must be the opposite. If one's an acid, the opposite's a base, or vice versa, okay? The next thing we're going to use is something called an indicator. An indicator is typically a liquid that we add in the bottom, and it changes color. Okay, yeah, that sounds kind of boring, but it changes color in an acid or a base. Okay, so again, if we know that the solution on the bottom is an acid, we want to see when it becomes basic, right? So we're going to add an indicator that's going to change color when it becomes something past a pH of 7. If the solution at the very bottom, our unknown, is an acid, then we want to see, or I said that, excuse me, when it's a base, we want to add this indicator that will indicate when it becomes acidic by changing colors. That will tell us and will indicate, hence the name, when it is neutralized at a pH of perfectly of 7. And it also tells us when we are finished, when that color change finishes. And that's basically neutralized. This is when the color change occurs. When the color change occurs, we know that we have neutralized. Occurs. It's only one R, isn't it? Sorry, I was thinking occurring or occurred, which is 2 R's. Apologize for that. Sorry, I'm getting confused. Let me just go ahead and put an S back. I don't know, I'm thinking and I'm messing up. Okay, so when the color changes occurs, that's when we are neutralized. So let's talk about the actual setup on the right side of the screen. Now the funnel at the very top is only needed at the very beginning in order to get our standard solution into what's called a burette. A burette is a very tall, fragile piece of glass that's a tube that could hold a known volume of whatever solution we want. So again, we know the, so in here, in the burette, we're going to put a solution with a known volume and a known molarity. Okay, so we know the volume, which I totally misspelled, and we know the molarity of that solution. Okay, everything about this is known. What we have down here is what's called an Erlenmeyer flask. And it's kind of triangular. And in the Erlenmeyer flask, well, we have, like it says, we're going to have a solution and the indicator. Neither of these do we know the volume. Well, we do know the volumes because we don't know the molarity. We don't know the molarity. So, and of course, this right here is called a clamp. It just holds it all in place so that we're very careful. Now, what we have here is a little valve, also called a stopcock. The valve we were going to open and close very gently. This is where it kind of goes from being a science to an art. What we're going to do, let's just again pretend that our standard solution is a base and our unknown is an acid. So what we're going to do is we're going to add our indicator first. So our indicator's in there. Notice it's pink. It's pink because, of course, acids are red in solution with this particular indicator. Now, this indicator that we're using is usually something called phenolphthalein. Let me just make sure I spell this correct because I can never spell it correctly. It has a lot of weird letters, and you'll see what I'm talking about. Phenolphthalein. There we go. So phenolphthalein is a very common indicator that we're going to use, and in the presence of an acid, it's pink. So that's why that little Erlenmeyer flask has a pink solution. But again, just to recap, it has an acid. We know how much is in there, but we have no clue how strong that acid is. Okay, that's what we're trying to figure out with the titration technique. Right above it, we have a burette full of a base, and we know the volume and we know the concentration. That's why it's our standard solution. So like I said before, we're going to very meticulously either swirl the flask or on a stir plate. A stir plate basically has a magnet in it, and then the magnet stirs electronically. Then we would put in a stir bar, which is plastic coated magnet, and it would go in the bottom of the flask, and it would spin as the stir plate has a magnet that spins. It would spin for us, right? It's kind of cool. Or we would just stir it with our fingertips very gently, okay? Again, the triangular nature of the flask prevents any splashing or anything getting too excited and going on the outside of the flask. Again, this is a acid in this particular example, so we do not want to get this on our skin. We do not want to get this on our clothes because we have no idea how strong this acid is. So the triangular shape of that flask really prevents any splashing or anything going too high up the sides of the container. So that's why we use that as opposed to just a rectangle or a square beaker, but the flask is more like this. So what we're going to do is we're going to open that valve very slowly, and we're going to drip in the base from our standard solution. Drip by drip by drip, very slowly. We're going to be swirling the Erlenmeyer flask. What we're looking for is the appearance of a color change. In this case, it's going to go from pink to clear, and then it could potentially go into blue. We want to catch it and stop it right when it gets to clear, because that would be the neutralization that we're looking for. From that, we will know how much of our standard solution did we add. We know the molarity, we know the volume, and we know the volume of this unknown. So all we don't know is the molarity. And again, you guys know that M1 B1 equals M2 B2. So if our base is our burette, we know the molarity, we know that, we know the volume that we added drip by drip by drip into the flask. What we don't know is the molarity of our unknown. We know the volume in this flask, we know the volume that was added to it, we know the molarity of the standard solution added to it. Again, what we don't know is our molarity of our final solution in here. That's what we're trying to solve for. So we're going to use the dilution equation, which again, you guys are already familiar with. You guys know how to do that. And we're just going to find the molarity of the unknown solution. So to do that, let's go ahead and try to go through a little bit more theory. So the graphs that result from a titration look just like this. And this makes a lot of sense if you think about it, because what we're doing here is we're starting with a pH really low, pH of 2. So that's a very, very strong acid. As we add volume, this is probably going to be 25 milliliters. We are still, again, pretty acidic around a pH of 2. When we get to a volume of milliliters, we're going to start seeing the pH change. Okay, the pH is going to start drastically changing. Okay, it's going to happen very drastically. We never get a graph that looks like this. They're always going to kind of go like this. Okay, that's just the way that it works. So this drastic change from pH of, I don't know, about 4 all the way. Now it depends. So here we have a very strong acid. If we add a strong base and we keep adding, we keep adding, we keep adding, it will eventually go all the way to 12 or beyond and kind of level out. Okay, but if we add a weak base to the strong acid, notice again, it's a strong acid. If we add a weak base, well, then it won't go quite as high. It'll level off lower. If we have even a weaker base, well, you guessed it, it would level off even lower, right? So that all makes sense because again, it really depends on the strength of the acid and the base that you are adding, that you are titrating. So that's what that looks like. Now, somewhere right in between, if we're doing maroon line, the equivalence point would be right about here, and I'll talk about that. If we're doing the green line, the equivalence point would be halfway, which is right about there. So how does the pH change during a titration? Basically, and generally speaking, if you are titrating an acid, let me say this more correctly. Sorry, I was trying to erase. If you are trying to titrate an acid, an unknown acid, with a standard solution of base, then of course the pH would increase. Right? Similar to what you see above on this chart. The pH is going to go from 2. Again, if we're doing the red line, it was going to go all up to 12. If we're doing the green line, 2 all the way up to 10. It's going to increase. But if you titrate a base with an acid, which again, you could do either way. It doesn't matter which way you go. Well, it does matter, but we have to know what we're doing, of course. But what I'm trying to say is the technique will work titrating an acid with a base or a base with an acid. We just need to know what we're doing, of course, but the technique does work for either type of solution. But in this case, the pH would not surprisingly decrease. The way that would look on our graph is we would have a graph like this, and it would look this way. We would start up here high on the pH scale, and as we add our acid, it would eventually go down. Again, if we add a weak acid, it would go here. If we add a super strong acid, it would maybe go down there. But again, that's what the curve is going to look like. So it either increase or decrease. It kind of depends on if you're going from titrating acid with base or base with acid. Lastly, again, is the equivalence point. The equivalence point is the point where your moles of titrate, I can't spell when I'm talking. Sorry, guys. Your titrant, which is what you titrated, equals the moles of substance in your unknown. Okay, so when the moles of the titrant, which you are titrating, equals the moles of the substance in your unknown, then you reach what we call the equivalence point, because of course they are equal, right? Okay, so let's go ahead and move on a little bit further. So what you see right here, guys, of these two graphs, again, is the equivalence points. So on the left graph, what we have here is we have a very strong acid that we're starting with, a very strong acid, pH of 1, and we're adding, again, by milliliter, we're going to be adding in sodium hydroxide, 1.1 molar sodium hydroxide. So that's a fairly low concentration of a strong base. So we're going to be adding it, drip, 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 drip. The pH is slowly starting to change, becoming less and less pink. And then a very drastic change. With just 1 or 2 drips, you can go from here all the way up to there. So you got to be very careful. As you're going through this part here, even though you're getting really impatient and you're like, gosh, I wish I could just open up this valve a little bit more and just kind of blow through that area. You don't do that, because with 1 or 2 drips, you will go from here all the way to there and you've blown it. You've messed it all up. You'd have to redo it or go in reverse, which is even more work. Then again, once you get here, if you keep dripping, 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 you'll get to a point where the pH, notice the pH really doesn't change as you go any further, because you've now gone all the way to the base side. But what I care about is if I'm going from 1 to about there, the equivalence point, which is halfway from here to here, halfway, is called the equivalence point. In this case, the pH of that would be 7. If you look over on the right side, we're going to start with a very weak acid, or a much weaker acid. Again, a pH of 3. That is about 100 times weaker than a pH of 1 on the left side. Again, we're still adding a low concentration of a strong base, 0.1 molar of sodium hydroxide in milliliters. We're measuring that in milliliters again. So we're going to be adding to our very weaker acid, not super weak, but weaker acid. And we're going to be dripping in base this 0.1 molar sodium hydroxide. So drip, 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 drip. Again, we're going to get a little bit of change, not a lot. We're just kind of waiting, being very patient, going drip by drip by drip. And we're going to look for a color change. I'm going to start seeing a color change, and then very quickly, it'll go from here all the way to there if we're not careful. And then after that, it's pretty much done, and you're not going to get any result. This area here is not informative. This area here does not tell us anything about the molarity of our unknown solution. So halfway between here and here is roughly halfway is our equivalence point. In this case, because we started with a weak acid, our equivalence point is a pH of about 8.72. Okay, guys? So again, that is all about titrations. Like I said, it is a technique where you can drip in an acid into a base or a base into an acid, as long as you know, again, you must know the molarity of your standard solution. You would need to know the volume of your standard solution. You would need to know the volume of your unknown solution, and what you don't know is your X, which is your molarity of your unknown solution. That's what we're looking for. Once we have all three of those numbers, we're able to calculate the molarity of our unknown solution, okay? Again, make sure you guys know about the graphs. Make sure you guys can interpret those. Make sure you guys can understand that you could titrate an acid into a base into an acid, and again, the behavior of what those curves would look like, whether it was a strong acid, strong base, weak acid, weak base, and so on. And also make sure you guys can identify where the equivalence point is located on the graph and how to find the pH of that equivalence point.